Ever since primitive times, humans have been using axes to chop wood. The first axes were simple sharpened stones, but when a handle was added about 35,000 years ago, it increased the force that could be applied with each strike, and that gave the axe much greater impact. Today, the axe hasn't lost its edge. Despite the proliferation of mechanized tools, it offers a low-tech, hands-on way to get the job done. A modern axe starts as a cylinder of high-quality steel. A ram nudges it into an induction furnace. The intense heat makes the steel white-hot and pliable, allowing it to be stretched and shaped. A powerful press then pounds the steel into a series of dies to further define the axe profile. A cutter head trims the edges. Operators now transfer the axe to another ram, which presses it into a die to straighten and level it. Then it's on to a revolving rack for a half hour to cool down and harden, just enough so they can be handled. A worker loads dozens of the axes into a tumbler. They are tossed about with tiny steel pellets, and the resulting friction rubs scale from the surface of the steel and also smooths the edges. Then this worker presses the back of the axe head against a sanding belt to bevel the edges. He sands the sides of the axe head for a smooth finish. In just seconds, he sharpens both sides of the cutting edge. It takes well-honed skills to do this with such quick precision. He then polishes the neck of the axe against a narrower, finer grit sanding belt. And it's time for a dip in a special solution heated to 1500 degrees Fahrenheit. They then quench the red-hot steel in warm oil. The abrupt temperature change hardens the metal, so it's tough enough for any woodchopping job. At the next station, a worker assembles pre-punched leather and plastic rings to build the axe grip. She places the black and white plastic rings at each end of the leather pack to give the grip a customized look. The rings get progressively smaller as she tapers the grip to fit the throat of the axe handle. It takes about 36 of the leather rings and 6 plastic ones to make one grip. She transfers the grip pack to an assembly press and inserts the lower part of the axe, which has been lubricated with beeswax, into the grip's center holes. A hydraulic ram drives it through. The lubrication ensures this job doesn't hit any snags. She now flattens metal prongs at the base of the handle to secure the grip. The axes rotate as a long abrasive belt rocks against the leather. It sands the grip to make the layers flush. A worker finishes off the job with a particularly aggressive sanding. His handiwork makes this grip look really smooth. A dip in clear lacquer brings out the grain of the various pieces of leather, and they appear to merge into one. Once the lacquer dries, another worker polishes the exposed steel against a belt with a very fine grit. The result is a glossy sheen that ensures this axe will definitely look good on the job. It takes about 2 days to make one of these axes, but they're designed to last a lifetime.
Granite is one of the strongest stones on Earth, and it's the darling of decor these days. As an indoor-outdoor building material, it's timeless, elegant, and resistant to acid rain. Nature's granite factory lies many miles beneath the Earth's surface. Boiling molten rock called magma builds up pressure from the intense heat and rises through cracks and crevices in the Earth's crust. As it rises, it slowly cools and solidifies into granite. Most granite is buried under sedimentary rock, which makes up most of the Earth's surface. The challenge is to extract as much granite from the quarry as possible, while losing as little as possible to damage from the extraction process. They start by outlining a section of rock wall up to 99 feet long by 23 feet wide. They use a gas flame to burn long, narrow channels to free up the sides. Then they drill holes 23 feet deep along the back and bottom. They feed explosive cables into the holes. Then they set it off. The explosion detaches the section. They then use a combination of drills, steel pegs, plates, and wedges to cut it down and cut it down further until they have rough blocks measuring 10 feet long by 5 feet wide and 5 feet deep, a size the granite factory can handle. The blocks may be small, but each one weighs more than 45,000 pounds. At the factory, the first cut is called slabbing. They use this type of saw to cut slabs more than 2 inches thick. The blade's metal segments contain synthetic diamond particles, which create the friction needed to make the cut. Water keeps the saw from overheating. It's a slow process. The saw cuts less than 22 square feet of granite per hour. They use a gang saw to cut slabs thinner than 2 inches, to make kitchen countertops, for example. This saw has steel blades, tense enough not to bend under the pressure of cutting, and calibrated to cut as straight as possible. The gang saw cuts at a rate of about 86 square feet per hour. It takes 3 entire days to cut through the rough block. Once a slab is cut, it goes for polishing. This is what will bring out the beauty of the stone. The polishing line has 19 heads, each of which has 6 bricks that polish by abrasion, like sandpaper. The brick grains get progressively finer as you go down the line. The polishing line processes about 10 square feet of granite per minute. For a high gloss finish, a slab goes through all 19 heads. For a semi-gloss finish, it goes through just the first 10 heads. For a rough finish, slabs skip the polishing line altogether and instead go through a process called flaming. With a stream of water to keep the slab from cracking under the heat, they run a propane flame at 2,000 degrees Fahrenheit across the surface. This intense heat makes the quartz inside the granite explode, creating a rough surface. They often use this technique for non-slip flooring. After the finish, the last step is to cut the slabs to specifications. Granite is composed of various minerals. They're interlocked like pieces in a jigsaw puzzle, giving the stone its trademark speckles and its remarkable strength. Those 3 little pigs knew what they were doing when they built that brick house. Not only are bricks wolf-proof, they're also fireproof, pest-resistant, and weather-resistant. No wonder they're one of the world's oldest building materials. Bricks are often made of shale, a lightweight rock that splits easily into thin layers. Quarry machines dig 16 inches down to expose the shale to the elements for 2 years. This weakens it, making it easier to process once it gets to the factory. A 4-foot-high stone wheel with a steel tire grinds the shale into powder. It grinds up to 50 tons of shale per hour. A screen sifts out pieces that need more grinding. The powder goes to the pug mill that mixes it with water. This makes a thick paste that will go through the extrusion machine next. The extruder forces the paste through a rectangular opening to form one long continuous piece called a slug. At the same time, it shaves off the crustier top layer to expose what will become the face of the brick. If this gray shale mixture is fired as is, it will naturally produce a red brick. To engineer a different color, they coat the slug in sand mixed with an oxide mineral such as zinc or iron. Next, they texture the surface with a textured roller. This is just one of many popular designs. Then a large knife comes down like a guillotine and slices the slug into 5-foot lengths. You might be wondering where those 3 holes came from. Well, remember how the paste goes through the extruder to form the slug? Inside are 3 pins. They make 3 holes designed to decrease the brick's weight. Out of each 5-foot length, they cut 23-inch bricks. The ones on the ends are uneven, so they go back into the mix to make new slugs. Next comes the delicate job of stacking these newly minted bricks to be. A machine first separates them. Then, using inflating bags, it grasps them, raises them, then stacks them. Meanwhile, the water in the bricks is starting to evaporate. To hasten that process, the bricks go into a dryer for 2 days. The dryer gets its hot air from the heat generated by the kiln, where the bricks go next for firing. The kiln is really a giant oven. It bakes the bricks at 1900 degrees. One and a half days later, the bricks are ready. The transfer machine takes them out of the kiln. But before they go to market, a technician does a quality check. He weighs and measures a sample to see if it meets the design specifications. Bricks are supposed to absorb some water, but not too much. Yet if they repel water completely, they'll also repel the wet mortars the masons use to stick bricks together. So to test absorbency, the technician breaks a brick in half. He weighs it before and after soaking it in water for 24 hours. By comparing the weights, he can see how much water the brick has absorbed. Once the batch gets the okay, they stack the bricks into cubes of 5 to 600. Each brick weighs 5.5 pounds, so each cube weighs in at about a quarter ton. Brick is one of the sturdiest building materials around. It doesn't rot, fade, warp, or dent the way some other materials can. Bricks are also energy efficient. They absorb heat to help cool your house in the summer and hold heat to help keep it warmer in the winter. There was a time when if you wanted to build something out of wood, you had to pick up an axe and go chop down a tree. Thankfully for city dwellers, all it takes today is a trip to your local home improvement center to buy 2x4s, 2x10s, you name it. They start with logs cut from spruce or fir trees. Turning them into construction wood isn't that complicated. First, they soak the logs for about 20 minutes. This removes the mud and softens the bark to make it easier to remove. Next, the logs go through the debarker, a machine with a rotor that shaves off the bark. The rotor has 6 sharp blades that take just 10 seconds to shave a log bare. In the filing room, they regularly sharpen and inspect the saw blades they'll use to cut the shaved logs, straightening them back into shape when necessary. In this sawmill, there are 2 production lines. The wider logs go through this saw. The worker at the controls uses a laser to help him position and reposition each log as he runs it through the saw several times to cut it into as many 4 by 10 inch pieces as possible. An average log usually yields about 7 or 8 pieces. The narrower logs go through a different saw. This saw first cuts a board off each side, then sends what's left off the log onto another saw. The 4 by 10s on the first production line go for a second cut, called the resaw. They're cut in half into 2 by 10s. The logs on the second production line end up here in what's called the Canterbull machine. It has 8 adjustable circular saws that can cut the log into various sizes of wood, anywhere from 2 by 3s to 2 by 8s, depending on the log's diameter. Both production lines feed to machines that smooth the edges and trim off any defects that can affect the strength or resistance of the wood. Then, an automated sorter drops the wood into bins according to their size. Each bin then feeds the stacking machine. From here, they'll put the wood into a kiln to be dried to about 15% humidity. Then they'll grade the pieces and ship them to a lumber yard or home improvement store. The earliest windows were merely holes cut into the walls. People living in warm climates left them uncovered, while people in harsher climates used animal skins to keep the cold out. In the Far East, people covered the opening with paper. Then came glass panes in sashes that swung in or out or hung one above the other. This type of window is called a casement window. A crank mechanism opens it at an angle. To build the window frame, the factory begins with 16.5-foot lengths of extruded PVC, a type of plastic. As clamps hold the PVC steady, a computer-guided circular saw cuts the sizes required for the frame. The same machine also cuts the pieces for the sash, the inner frame around the glass. Each frame is made from 4 pieces whose ends are mitered at a 45-degree angle. Now workers load 8 pieces onto a computer-guided welding machine. 8 because it welds 2 frames at a time. First, a heating block, whose temperature is 446 degrees Fahrenheit, melts the ends. Then the machine pushes them together. They fuse, forming the frame's 4 corners. Here's the same process viewed from above. As the melted ends bond under pressure, excess PVC oozes out at the joints, then hardens. The next machine will clean that up. A robot reads the profile of the specific frame style. Then it uses one of several cutting heads to shave the excess off the corners. From here, the sash and frame go to another area to receive hinges. Meanwhile, workers cut the glass to size. They start with a huge sheet measuring about 6.5 feet by 10 feet. It's very heavy, about 200 pounds. So they lay it on a specially designed table. A blower sends up air through tiny holes. This floats the glass just above the surface, making it easy to move around. They score the glass using a sharp carbide cutting wheel. This window will have what's called a thermopane, 2 panes of glass with argon gas in between for insulation. One of the panes has a transparent metallic coating to reflect the heat back into the house. They adhere a strip of silicone foam around the perimeter of the first pane, notching it for a good fit around the corners. The foam is covered in a thin, strong polyester film to prevent the gas from leaking through. The strip is a spacer, creating a gap between the 2 panes that's just over a ½ inch wide. That's where the gas will go. They cut a hole at the top of the spacer and another at the bottom. You'll see why shortly. This window features decorative grid work called muntin bars. They're made of aluminum and go between the 2 panes. A worker lays the bars onto the first pane, then uses this guide to line them up perfectly straight. Then she puts the second pane on top. It sticks to the exposed adhesive edge of the spacer. Now the double pane glass goes through a press, whose rollers apply pressure to ensure a strong and thorough bond to the spacer. After the glass exits the press, workers pump in argon gas through that hole at the bottom of the spacer. The speed of the gas flow is critical. If they pump it in too fast, it'll mix with the air in between the panes, rather than push it through the hole at the top of the spacer. After plugging the holes, they coat the spacer in a polyurethane sealant. This makes the thermopane completely airtight. Now it's ready to go in the sash. A piece of PVC called the glazing stop holds it there. They snap it in place using a roller. A little PVC cement to seal off any minuscule gaps in the corners, then the sash goes into the window frame. Their respective hinge parts simply snap together. The last step is to snap the frame's crank arm onto the sash. Chains are as indispensable today as they were thousands of years ago. Ancient historians referred to the use of metal chains for jewelry, shackles, and construction. Today, chains are used for those very same purposes and many more. Chains are used to tie things down, hold things together, and pull things along, and their many sizes reflect the varied uses. To make a chain, a turning drum uncoils this wire rod and pulls it through a steel guide ring to a steel draw box. Grease inside the box lubricates the wire. On its way out of the box, the wire goes through a die, such as the one being demonstrated here. The die has a smaller diameter than the wire, and as the turning drum pulls it through, the wire narrows, hardens, and becomes stronger. Now, electrically driven tools move in from all sides. This is a forming machine. A tool called a jaw propels the wire forward, while another jaw pushes on the wire, bending it around a steel pin. It forms a C shape. Another forming tool closes the C, completing one link in the chain. And then another jaw makes the next link. This machine is making jack chain, which is usually used to hang lights. Another forming machine makes a chain that can haul a heavier load. A grip pulls the wire onto rollers that straighten it out. Steel cutters now make notches on both sides of the wire. These notches mark the place where the wire is to be sliced into link-sized pieces. A mechanized knife makes the final cut at the notches. Next, roller arms loop a cut piece of wire around a steel finger. The roller arms make it look easy, but they're actually exerting tons of pressure in order to shape this wire. After the rollers form the link, a pliers-like tool grabs it and turns it around. This positions the completed link so that it can connect with the next link as it's shaped. As each link is added, the chain drops into a pile below the machine. There are dozens of forming machines in most chain factories. Each machine makes 50 to 60 links per minute. That's about 250 feet of chain per machine hour. To put that into perspective, one machine could make a chain as long as the Empire State Building is high, in just under 6 hours. After the chain is formed, it will need to be strengthened. So it's on to the welding machine. Hammers to the left and right push the link in. Then 2 copper blocks move in from the sides. They act as electrodes and zap both sides of the link with an electrical current. The current ripples through the gap in the link while the hammers push it in. The link reaches a scorching 1700 degrees Fahrenheit. The wire melts and the link fuses together. Now a pulley system drops the freshly welded chain into a heat-treating coil. An electrical current runs through the copper coil, heating the chain inside until it's orange-hot, 1724 degrees Fahrenheit. The pulleys lower the chain into a tub of water to cool. The extreme temperature change alters the molecular structure of the steel, making it much harder. But the experience leaves the chain a bit brittle. So it goes into a second heat coil that's not as hot as the first one, and then into another cool bath. This takes away the brittleness and gives the steel a bit of stretch. Now the ultimate strength test. This is the chain calibrator. Pulleys run the chain into a groove that's been cut into a block of steel. A clamp on the left holds it in place, while the hydraulically powered block of steel pulls the chain to the right. Will it break or will it hold? And can it handle the load? After all, the chain is only as strong as the weakest link.
They call Superman the Man of Steel because, flying an X-ray vision aside, he could bend solid steel with his bare hands. Thanks to its legendary strength, steel is used for everything from bridges and skyscrapers to household appliances. Steelmaking usually begins with a pile of scrap metal. Using this 11-ton electromagnet, scrap iron composed of crushed car bodies, electric appliances, cans, and other steel scraps is gathered up. This powerful magnet is able to lift 5.5 tons of metal.
About 83% of this scrap will be transformed into bars of steel. This metal is then dumped into a basket which by itself weighs 35 tons. The basket can hold up to 65 tons of metal. And now they're going to melt the metal. This furnace reaches a temperature of 3,000 degrees, hot enough to liquefy the metal. It is heated by 3 electrodes and by 4 natural gas burners. The contents of the basket are dumped into the furnace. Here, the pieces of metal come into contact with liquefied steel, which always remains at the bottom of the furnace. There's a reaction and an aeration system draws out the smoke that's produced. At this high heat, the 66 tons of metal will melt in about 60 minutes. Then the cover is placed on the furnace. This liquid is composed of impurities that rise to the surface when the metal becomes molten. At this stage, a workman draws a sample of steel to determine its chemical makeup. And now they make use of a supersonic oxygen lance. This lance blows oxygen into the molten steel. This reduces its carbon content, homogenizes the mix, and speeds up the melting process. A ladle is positioned beneath the furnace. The molten steel will be transferred from the furnace into this ladle. The molten steel easily pours into the ladle. The ladle weighs 60 tons and holds 127 tons of molten steel. An overhead crane capable of lifting 200 tons carries the ladle filled with steel. Additives are introduced in order to obtain the correct steel tone. Here, the electrodes are taken out of the furnace ladle. A workman now opens the pouring nozzles of the distributor. It is equipped with 4 pouring holes. The molten steel runs into molds. It cools very quickly and begins to harden. Steel billets are produced in lengths varying from 15 to 35 feet. The billets are then cut to the desired length with a natural gas torch. A pouring identification number is marked on them with a wax crayon. The difference between a steel billet and the nearly finished flattened product is clear. Flattening of the billets remains to be done. Before flattening begins, billets are placed in the furnace to be reheated for 2 hours at 2,000 degrees. Water jets cool the billet ejector. The billets are placed on the flattener, where powerful rollers compress them. This operation gives the billets the required shape and size. Water-cooled rollers crush the billets. Some billets go from a thickness of 5 inches down to ½ an inch, while others reduce from 6 inches down to 3/4 of an inch. At the end of production, bars move along at a speed reaching 22 miles per hour. Once they reach their required dimensions, the bars must be cooled. This cooling bed allows the steel bars to cool uniformly. A total of 440,000 tons of steel bars are made at this plant each year. Anyone with a green thumb knows that it takes both skill and patience to make a garden flourish. It also helps to have the proper tools on hand. An avid gardener's arsenal can contain everything from shears, trimmers, and pruners to rakes, hoes, and spades. The handles of these garden tools are made of white ash, a sturdy wood that can withstand the force of shoveling, digging, or raking. These dried ash dowels measure 2 to 7 feet long, depending on the tool being made. They first enter what's called the chucking line, where specially designed automated machines shape them into handles. The first operation rounds the dowels to the required diameter. about 2 inches depending on the tool. The next operation cuts the dowels to the required length and profiles their ends. Two chucking heads, one on each side, carve the ends simultaneously. One shapes the bottom of the handle to fit the tool's blade. Certain blades go over the wooden handle, while others go into it. For inserted blades, another chucking head hollows out the handle. Meanwhile, the chucking head on the other side rounds off the top of the handle. The finished handles spin against a sanding belt as they exit the chucking line. This smooths the surface of the wood, preparing the handles for a coat of protective varnish. High-end shovels and spades have what's called a steel D-grip, a steel handle grip with a wooden insert. An automated lathe first shapes a piece of ash to the right length and profile. Then an automated drill pierces a hole. To make the sides of the grip, workers begin with 2 pre-cut pieces of steel called blanks. They place them in a manually operated press that shapes them in a 2-step process. They use the heat of a strong electrical current to melt the steel and fuse the pieces together. This is called resistance welding. Next, they feed a steel rivet through the sides and wooden insert, and fasten everything together. Elsewhere in the factory, a heated forming machine stamps out the steel blanks that workers will shape into blades. A robotic arm loads the blanks into an oven. In just 4 minutes, the oven heats the steel to over 1800 degrees Fahrenheit. This intense heat makes the metal malleable. Workers then take out and shape one blank at a time. They only have a few seconds to form the steel before it cools off. The first press forms the blade, in this case a shovel, and a partial socket. Then the second press closes the socket. They quickly submerge the blade in lukewarm water to cool the metal down. By now, the steel is extremely brittle, so the blades go into what's called a tempering furnace for 15 minutes. This alters the metal's internal structure, restoring its strength. The steel D-grip has been cleaned and painted. Workers insert the wooden handle and nail the parts together. On the other end, they attach the blade, which by now has been varnished to prevent corrosion. After drilling a hole through both the metal and the wood, they fasten the blade using a rivet if it's a high-end tool, a nail if it's a budget model. These hot-off-the-press garden tools are finally ready to put in a hard day's work.